Okay, fairly short section on colored complexes, kind of trying to explain why transition metal compounds and complexes are often colored. So it's all about splitting of these D sublevels, and we're going to explain how that splitting relates to the color and the type of color that we're seeing. So just as a start, zinc itself, of all this line of D block elements, zinc isn't really called a transition metal because it doesn't form an ion with a partially filled D shell. So the only ion that we see for zinc is Zn2+. And if zinc itself is 3d10-4s2, whatever's before argon, then our Zn2+ is 3d10. That's it. So it's got a full D shell, and for reasons you'll see on the next slide, that means we don't get any of these magic transitions, and as a result we don't see any color there. So zinc compounds tend to be white. So where does this color arise from? Well, if we take our transition metal as an octahedral coordination, so in other words we've got our central metal, and then we've got one up, one down, we've got two going back, two going like that, then these are our d orbitals. And so we've got our ligands in each of these positions, and the metal of course has its own charge of some sort, and some of these orbitals, these are the shapes of the d orbitals, you don't need to remember these shapes, but some of these orbitals will point directly at the ligands, like this one and this one. Other ones point in between the ligands, right? So their energies are different. These ones that are pointing in between are of lower energy. See a group of 3 here. These ones that are pointing directly at the ligands are at higher energy. So if we come out of, this would maybe be our gas phase for our transition metal ion, and we're over here as an aqueous solution, let's say, then we've got the possibility where our electrons can move between these two levels. And so this is quite a small gap in energy, but what's required is some energy to get this excited up to the next level, and that energy comes in the form of light, right? So we get some light shining on it. It might be that that transition, the absorption, corresponds to one of the frequencies within the visible region, right? And if that's the case, then the light that we see coming back, so if this had all the colors of our rainbow coming in, then some of them get absorbed and the rest are reflected, and we end up seeing the reflected color. So there's an eye, there it is, very bad drawing, but some of the light that's gone in has been absorbed to affect this transition, and then the rest of the light is reflected away, and that's what we see. And that gives us this idea of complementary colors. So if you think of a leaf, why is a leaf green? Plants tend to be green because they are absorbing, the chlorophyll that's in them is absorbing all the other colors. The green color is not used, so that's what you see, that's what gets bounced back, and that's why trees appear to be green. And we can use a similar argument, it's not perfect, but we can use the same idea in chemistry, and this is in the data booklet. If something is absorbing in this region, let's say it's absorbing in the violet region, then we're likely to see a yellow color. If something is absorbing in the blue region, we're likely to see an orange color, right? This idea of complementary colors, things that aren't taken in and absorbed. So the size of that splitting is obviously going to be very important as to which color is observed, and there's a couple of factors we need to look at to decide on what affects the size of that splitting. And the first factor is, well, what is the ligand? What is the ligand that's attached to it? Where is it in this spectrochemical series? Because some substances, like these ones, strong field ligands, cause a large splitting, right? They give you a larger splitting between those d orbitals, bigger dd splitting. Others, so these strong field ligands will give you a big splitting. These weak field ligands will give you a smaller splitting. So if we've got a bigger gap up this end between those Ds, then we're going to be seeing higher energy, we're going to be absorbing at higher frequency. So if we're absorbing at higher frequency, So we're absorbing this area of the spectrum. We'd maybe expect to see more of those colours there. Another factor that can affect the colour that we see is the metal ion itself. So what is its charge? So if we've got a bigger charge, higher nuclear charge I should say, then we tend to get stronger interaction with the ligands, and again we get a bigger splitting. And we can also consider how many d electrons are there, because that can also affect the splitting. And you can see two examples here, that the iron 2+ is absorbing in violet, whereas the iron 3+ is absorbing in the blue. And using the colour wheel, you can see what colour those are coming through. That's what we've covered. That's the references. Thank you.